In our video today, we're going to be looking at two topics. We're going to be looking at the determinant of a matrix, and we're going to be looking at the inverse of a matrix. First topic we're looking at is the determinant, which in a sense is kind of like the size of a matrix. So let's look at an example of how this is done. So the determinant only works when we've got what we call a square matrix, where the number of rows is equal to the number of columns. And we're actually only going to look at doing these by hand when we've got a 2 by 2 matrix. So here we've got matrix A, which has 2 rows and 2 columns. And when we want to calculate the determinant of A, which we can write det A, that computation we're going to do by taking entry 1, 1 and multiplying it by entry 2, 2. So we get 3 times 4. And then we're going to subtract our product where we take entry 1, 2 and multiply it by entry 2, 1. So we're going to do minus negative 2 times 1. I'll put that in parentheses so we keep track of the fact that we're going to be doing minus and negative. So we'll get that this is 12 minus negative 2, which means that our determinant then is going to be positive 14. So quickly we'll do one more example. Here we've got matrix B, and we're going to compute the determinant of B. So we will do 3 times negative 14 is negative 42, minus negative 7 times 6 is negative 42. So we'll get negative 42 plus 42 is equal to 0. So the determinant of B is equal to 0. Now, as I said at the beginning, these determinants are kind of like the size of a matrix. Don't worry too much about that, except to say that when we get a matrix with a determinant equal to 0, that's going to have a very particular property that we're going to talk about with the next topic, which is the inverse of a matrix. Now I'll do one more, not exactly an example here, but sort of the general rule for determining the determinant of a matrix. So if I've got a matrix M, which is equal to values A, B, C, D, then the determinant of matrix M is just A times D minus B times C. So if you're okay with everything before I introduce this matrix M, stick with what you were doing, but some people like to have this rule for the more general matrix M. So there it is available to you if you'd like to use it. Now the reason we care about the determinant is because it allows us to compute what we call a matrix inverse. A matrix inverse is something that we can multiply a matrix by that essentially gets us a 1. If you remember back to the 4.2 assignment, there was that matrix I we multiplied by that kept the original matrix we were multiplying by the same. So this matrix I sort of functions like 1 when we multiply normal numbers. Let's do an example to see what we mean. So here I've set up some matrix multiplication to multiply a matrix A by matrix I. This matrix right here is the 2 by 2 identity matrix. It's 2 by 2 because it's 2 rows by 2 columns, and it's the identity for reasons that we will see. Then when I do this matrix product, A times I, well, I'll get for this first entry 3 times 1 plus negative 7 times 0 is just 0, so this is just going to give me a 3. Then for my entry 1, 2, I'll get, let's see, 3 times 0 plus negative 7 times 1. It's going to give me a negative 7 there. For my entry 2, 1, let's see, I'm going to get 1 times 1 plus 2 times 0, just going to give me a 1. And finally, for my entry 2, 2, I'll get 1 times 0 plus 2 times 1 is just going to give me a 2. So as you can see, the matrix A times I that I've got right here is exactly the same as the matrix A I started with. So this I, the identity matrix, if I multiply it by the proper size matrix, I produce the same matrix. So it's behaving like a 1 when we do normal multiplication. Now if I have a matrix A, as I've indicated here, with entries A, B, C, and D, to compute the inverse matrix, I will need to do two things. First of all, I need to compute the determinant of A. I'm going to be multiplying a matrix by 1 over that determinant of A. And the next thing I'm going to be doing is I'm going to be taking D and A and swapping them here and making my B and C negative here. So this might be a little confusing at the moment, but I think it'll clear up when we do an example or two. So here I've defined matrix B, and pretty quick computation should show us that the determinant of B is going to be equal to -6. So to compute this B inverse, which we write as B to the negative first, we're going to have a 1 over -6. That was our 1 over our determinant, which we had up here, is right here. And then we are going to take the top left and bottom right entries and swap them. So I'll have a -3 here, the 2 here. Then I'm going to take my top right and bottom left entries and make them negative. So this will become a -1. This will become a -0, but that's just 0, so I'll leave it as is. So there's my inverse matrix, and if I really want to, I can multiply the -1/6 in, or I can leave it written as it is. So I could also write this as -3 divided by -6 is 1/2. That'll be 1/6, 0, and -1/3. And so there are two acceptable ways that I could write this inverse matrix. And the neat thing about this inverse matrix is that if I take B and I multiply by B inverse, the matrix I'm going to get is that identity matrix that is 1, 0, 0, 1. That's what I'll get if I multiply any matrix by its inverse. So we'll do one more example. Here's matrix A, entries 2, -5, -1, 3. Hopefully a quick calculation tells us the determinant of A is equal to 1. And so then we can write A inverse is equal to 1 over 1, the determinant of A, times 3 and 2 get swapped, and the -5 and -1 get made positives, so we've got the following matrix. Now I chose determinant of A equal to 1 for this, so we have an easier computation here. So this is really just 3, 5, 1, 2. Now, I claimed that if I multiply A and A inverse, I should get that identity matrix, and we'll actually confirm this with this example. So if I do A times A inverse, well, that's going to be equal to, for entry 1, 1, of 2 times 3 is 6, plus -5 times 1 is going to give me a 1. For entry 1, 2, I'll have 2 times 5 is 10, plus -5 times 2 is -10, is going to give me a 0. For entry 2, 1, I'll have -1 times 3 is -3, plus 3 times 1 is +3, add those together I get 0. And finally, for entry 2, 2, if I do -1 times 5, that's -5, plus 3 times 2 is +6, gives me a 1. So I do end up getting this 1, 0, 0, 1 matrix, and it turns out that I'll get the same thing if I do A inverse times A. To remember, multiplying matrices doesn't always work the same. A times B is not always the same as B times A, but in this case it is true that A inverse times A is equal to A times A inverse, which is equal to that identity. So I think that's all we've got for the lesson in this video, and I'll give you a couple practice problems to prepare for class tomorrow. So here we've got two matrices. I'm going to ask you to find the inverses of each of these, and that should be pretty quick, and I'll see you in class tomorrow.